Okay, Algebra 2, we're back here and we're going to be doing some rationalizing the denominators, okay? And this involves fractions, not everybody's favorite, but hopefully it makes sense to you after you watch this, okay? So if you watched my previous video about multiplying and dividing radical functions, you guys would have seen that there are some times that we can really easily simplify the radical, okay? So, because there's a rule that says, like for ones like this, um, there's a rule that says as long as the radicals have the same index or it's the same type of radical, like they're both square roots or they're both cube roots or whatever, you're allowed to kind of change this. So I could rewrite this as one big radical and write both of these, the top and bottom of this fraction, inside that. So this would be the same as the square root of 35x to the fourth over 5x, okay? And then I can kind of reduce this fraction, okay, because we have some numbers that can reduce, right? So 35 divided by 5, I could say that's 7, right? And then x to the fourth divided by x, right? The same type of variable. So I can do x to the fourth divided by x to the first. That leaves me with x to the third, right? And again, this is a little bit of a review because I want to compare this to a problem like the one we have below. But the last thing I could do here is, right, I have three x's in here. Or another way I could say this is 7xxx, right? And so again, I have this two of the same type of term or number, right? So when I have a pair of that, I can pull that out of the radical, right? So the fully simplified version of this would be x times the square root of 7x, right? That single x just left in there, okay? So again, we went over that last time, but I want you to compare that to a problem like this. And this is the one where we're really going to have to worry about rationalizing the denominator, okay? Because, right, a problem like this, it canceled because I was just able to reduce the values from the fraction because it worked out pretty nicely. But for this one, look at my terms here. I have the cube root of 5x squared, okay? And then on the bottom, I have the cube root of 12 y squared z, okay? Now there's a couple problems here, okay? They're both the same index, so I am going to be able to sort of change this and get this radical out of there, but I'm not going to be able to do it this way because 5 and 12, right? If I did 5 divided by 12, I would get a decimal, and there's not really any common factors there either other than 1, so I can't really reduce that. And with my variables too, there's an x in the top fraction or top radical, and then there's a y and a z on the bottom. So lots of issues here. That means I can't simplify it like I did up here, unfortunately. Okay, and so this is where the strategy of rationalizing the denominator is going to come into play. Okay, so what I can do here, okay, again, the first thing you want to look at is what type of root it is, what type of radical. And this is a cube root, right? And so in this case, right, again, my focus is on the bottom, okay? Kind of like when we were dealing with complex numbers and imaginary numbers, I was just focusing on the bottom. It's going to be the same thing here. Okay, so here's what I do. I'm just focusing on the bottom. Again, the top can be whatever, okay? Because if I'm simplifying this, the top doesn't matter. The only rule I'm worried about is that one. You can't have radicals in the denominator. I look at my terms in here, okay? And basically, what I want to happen for this cube root, this radical to go away, again, think about this. If it's a cube root, this is kind of separate, but if this is a cube root, let's just think about just my variables first. Y squared, right? If I was to expand that, or to say like y, right, that wouldn't be enough to pull the y's out of the radical, right? Because I need 3 of them, because my index is 3 here, okay? In my z too, I just have one z. Again, that would have to stay under the radical right now because I would need 3 z's to be able to pull that out of the radical, okay? So I don't have enough variables, okay? In my 12 here too, that's a little bit separate. But again, just my variable part, let's think about this. Say I had a third y in here, and say I had 2 more z's. What would happen then? Okay, what would happen then, right, is that, okay, I could take those 3 y's and pull it out of the radical, and take these 3 z's and pull it out of the radical. Okay, and then I'd be left with y and z, because I would take the cube root of those 3, and it would kind of cancel, and I'd be left with just a y and a z, not under the radical, right? So that's what I would want to happen, okay? Now I have to think about, okay, how many y's, right? I just added one y in here, and I added two z's in here to be able to make that happen. Okay, and so I'm going to have to multiply by the cube root. Again, we're going to deal with the number, the coefficient here separate. So if I multiply this by the y and z squared, or two z's, again, if I multiply it by this one, that will give me the three y's and the three z's that I need for the radical to cancel with the variables, okay? Now, I want to do the same thing with the number that's under here, okay? Now, something you could do with the coefficient here, okay? Now, again, I just have 1/12, so this would be right now the cube root of 12. Okay, again, the cube root of 12, there's just 1/12 there. But say I had 12 times 12 times 12, that would be 3 12s, and I could pull that out, right? So it's the same idea. I would, again, I just have that single 12 under there, but I would need to add in these two 12s under the radical. So again, I would need to kind of include in this what I'm multiplying by, I would need to include two more 12s, or a 12 squared. And you could write that as, 12 squared is 144, and you could rewrite it like that, but almost writing it as 12 squared is almost a little bit simpler, right? So that's what I would multiply by. And if I would multiply it by this, that would give me 12 cubed, or 3 12s, 3 y's, and 3 z's, which will give me a group of 3 of all of them, and I'll be able to pull them all out, which will be awesome, okay? Now again, anything with fractions, to make this legal and to make this okay, I have to multiply by kind of a version of 1, because that isn't changing this, right? If I'm simplifying something, I can't totally just change it. I have to multiply by the same thing on top and bottom. So on the top too, 12 squared y z squared. Okay, so that's what I begin with. I begin with figuring out, okay, how many of each term, each thing in here do I need to multiply by to make it a group of 3, or a group of whatever the index is. And now let's multiply those, okay? So I'm going to get a big fraction. The bottom is going to result in 12 times 12 squared would be 12 cubed. Y squared times y is y cubed. Z times z squared is z cubed. And again, that is going to all cancel out with that cube root, and I'll be good, okay? But on the top here, there's that rule that says I can kind of write this as all one kind of big thing. And so I could multiply 5 times 12 squared. And in this case, I am going to write it as 144 to make it a little easier to understand. So I'll do 5 times 144, and then I'll do x squared, right? X squared times y, and then times z squared. That's not really gonna, I just basically am gonna lump all these letters together, because none of them are in common to multiply. So that's what I would have left, okay? And so now I would continue, right? I could continue here. Just let's re-simplify the top. Okay, let's just multiply these. So 144 times 5 ends up giving me 720. Okay, and then that, again, all these variables, none of them can cancel with each other. Okay, so that's all going to stay the same. Now, unfortunately, I'm not done with the top. There's a little bit of ugliness left to deal with there. But on the bottom here, again, this is why I did this way. Again, the bottom, the cube root is going to cancel with all these 3 exponents. Because again, if I expanded this, this would be saying 12 times 12 times 12, y times y times y, z, z, z. And so that would be a group of 3, and all those would come out of the radical. So what would be left on the bottom would be 12 y, z. And again, that's what I want to happen. That's good. Now, the only ugly part that's left with this problem is this cube root of 720, okay? Because again, if I'm simplifying this all the way, I want to reduce that radical, right? And 720 is a number that has perfect cube factors, okay? So again, thinking about your perfect cubes, again, these are the first 5, there's lots more, but again, these are the ones I mainly want to focus on and think, okay, with this cube root of 720, are any of these numbers, right? Could I multiply one of these numbers times something else to equal 720? And I know for sure I can with 8, so let me start with that. 8 times what is 720? It'd be 8 times 90 is 720, okay? And so 8's going to be a perfect cube, okay? So I could say the cube root of 8 times the cube root of 90, okay? And then the cube root of 8 is just 2. and then the cube root of 90. And then I would think, okay, the cube root of 90, does that have any perfect cube factors other than 1? And no, actually, it doesn't. You can't multiply any of these times something else to get 90. So this one's pretty easy to simplify, but there are ones that are a lot tougher. Okay, so almost done with this one. So what I would do is I would rewrite this. Let me kind of box that off. I would rewrite this as 2 times the cube root of 90 x squared y z squared, okay, and then over this 12y z that's on the bottom, okay. And my last step here, I'm just about done, okay. You might notice because I pulled out this 2, again, I can't simplify a number that's in a radical with a number that's outside the radical, okay. So like I can't reduce this 90 with this 12, but this 2 and 12, this 2 is outside of the radical now, and this 12 is here. So I can divide both of these by 2, okay. So my final answer is going to be over here, the cube root of 90 x squared y z squared over, again, divide both of these by 2, so it'd be 6y z, okay. And that is my final answer, okay. And again, your goal is achieved because there are now no more radicals inside that denominator, okay. So that's a really long one, and that was tougher because it had cube roots. Maybe I'll just go through one more like that over here, and then we'll be all done, okay? Okay, so now we're looking at number 3, and I made it a little bit simpler because this was a really long and messy one, number 2. So we'll go a little bit quicker with this one, okay? So again, the first thing you want to do is look at that bottom of the fraction, and you think, okay, it's a cube root, and I have a 5 and a y, okay? So again, you're kind of thinking, okay, if that is how many I have right now, how many of each of those would I need to complete the group that I need to be able to pull that term out of the radical, okay? So again, I would just have a single 5, okay? So I can't really expand this anymore because there's no exponents or anything. So 5, okay? And so to complete that, to make it a group of 3, I would need to add 2 more 5s to that, okay, or 5 squared. And same with y. I just have a single y under there. And so to complete it to be a group of 3, I would need to add 2 more y's in there. Okay. So again, that's what I'm going to multiply by. I'm going to multiply by 2 5s, or 5 squared. I'm going to multiply by y squared, 2 y's. Okay. Because again, that will complete this to make it 5 cubed y cubed, and that will make it groups of 3. I can pull those out of the radical. Okay. Now again, I have to multiply the top by the same thing. So again, 5 squared, or again, it's kind of, you can write it either way. They're the same, right? So then I actually do the multiplication, right? So I'm going to multiply, again, bottom first, because that's kind of what we're focusing on. On the bottom, I have 5 times 5 squared is 5 cubed. That's what we want. And then y times y squared, y cubed. Again, that's what we want. So good. That's good. And then on the top, again, I can kind of group everything together. So 6 times 25, I'll just do that real quick. And so I'm going to multiply on the top here. And so I'm going to do 6 times 25. Here's how I like to do multiplication with 25s. I think, okay, how much money would I have if I had 6 quarters? And I would have $1.50. So 25 times 6, 150. So mental math, you guys can do that. And then again, x squared and y squared, can't multiply those together, so I just kind of lump them at the end. Okay? Now, I simplify, right? So again, on the bottom here, this cube root is going to cancel with these 3 exponents. I have groups of 3, so everything is going to come out. And it's going to be 5y, okay? And then again, this 150 x squared y squared, I think, okay, does that have any perfect cubed factors out of these? Okay. And no, it does not. It doesn't have any perfect cube factors. Okay, so it's actually going to remain cube root of 150 x squared y squared. You might be thinking, oh, 25, couldn't you break it up like that? 25 is a perfect square, perfect cubes. It's a whole different ball game. So that's why I like to have these up on the side to kind of remind me, and so I don't mix them up, okay? So this would be my final answer, okay? And again, you might be saying, oh, couldn't you do 150 divided by 5 or y squared divided by y? No, you can't, because again, these are under the radical up here, and these are not in a radical. So You can't kind of take, you can't reduce things that are inside with things that are outside. Okay. So that's it. That's a little taste of rationalizing the denominator. We'll do a different scenario where we'll have to rationalize a different way as well, but we'll save that for another one. So thanks for following. Hope it makes sense. Good job.